more parameters, introduce kinetics to the problem, probability to the problem, and then I solve it. Finally, I discuss the Dolce. So these are the main code where the blue 4 lines, 5 lines, and the last bit in red. Finally, I will give you the summary of the code. So, what is fractal? To understand fractal, we have to understand first what is not fractal. The history of geometry actually is as old as the science itself, and it is associated with the Euclidean geometry that restricts us, our boundary of our imagination, to a line, to a circle, parallelogram, squares, spheres, etc. etc. The things that I just mentioned, line, square, rectangle, sphere, circle, parallelogram, all these have one thing in common. What is that? If you double the linear size, if it is a line, mass will increase by a factor, also double, will be double. If it is a square, if the linear size is increased by a factor of 2, mass will increase by a factor of 4. If you increase by a factor of 3, mass will increase by a factor of 9. So you can put them in one equation like this, which is called mass-length relation. So if it is a line, we put d equal to 1. If it is a square, we put d equal to 2, and so on and so forth. Now, another quantity of interest is the density. What is density? Density is the mass of the object divided by the ratio of the mass of the object and volume, not of the object, the space where the object is being embedded. So mass of the object and the volume of the space where the object. So for every object, you need a space to embed this, right? So volume of that object is, so mass from that relation and volume is this relation. So that defines ultimately the Euclidean object. What does it say? Is that density is a constant. What does that mean? So if I give you infinitely many indistinguishable points of balls, marbles, indistinguishable particles, and I ask you, decorate them, making sure that it is a line, so the dimension is equal to 1. Decorate them in a plane, embedding space is a plane, in such a way it creates an object which is dimension 2. Or decorate them in a space in such a fashion that it constitutes an object which is dimension 3. What would you do? You would ensure, so you put them, if you make a line having for a dimension 1, you put them like this. What are you making sure? Number of points per unit length constant. What is the distance between points is immaterial. So you can put like this, or you can put like this, dots. They will still constitute a line or a square lattice line. When I say ask draw a square lattice, the distance between points is immaterial. Okay? So what is the density of the points? So when you decorate them, you make sure the density of the points is constant. So that is the takeaway message from this slide. That how do you constitute a Euclidean object? You make sure that density of the points of the object is uniform, constant. Is that clear to everyone? Okay. For example, this statistically uniform distribution. So it's a visual impression what to expect, to consider an object as a non-fractal, a Euclidean object. Now, little bit of math. Physics is all about measurement. So, if I give you a line, I ask you, so we need to know something measure. And when question comes to measure something, we need an yardstick. So, if it is a line, then I measure 1, 2, 3. So, I measure and I tell you that it's a number. When I say the number, if you know the unit scale, if it is millimeter or centimeter, if you have an idea about that, number will give you an impression about the size of the object. Okay? So, if it is a line and you measure delta, the number is obtained by L by delta. Now, if delta size, if I half it, so I can reduce the size of the delta by a factor of n, and I can measure the number. So now the number, new number, is increased by a factor of n from the original one. Is it clear? If you do the square, the new number will be increased by the original from by n square. If you do a cube space object cube, it would be like n cube. So I can generalize the expression. So n delta by n, if the yardstick, so when you have a square, I ask you measure this board. What you do? You cannot measure this with a line. You need a square. So you put 1 square, 2, 3, 4, you measure. And then you half the side and you measure the number. New number, now the number that you find will be increased by the previous number by a factor of n square. Is it clear? So I can generalize for any d dimension by this equation. This is called homogeneous function, because a function that satisfies this relation, if you increase the factor x by a factor of lambda, the function is multiplied by lambda equal to p. Here lambda is the homogeneity factor. A function which is homogeneous in this fashion has only one solution. Function must have a solution, a power law solution. That is, mathematically we can prove it by 10 lines. Okay? Power law solution. So you can map this as a, so that this is also a homogeneous function, which implies the solution for n must be a power law. Indeed, if you plug this is the solution of that equation. If you plug it here, you will find right hand side and left hand side matches. So that solve the equation. So n delta equal to delta 2 minus t is the solution of that equation. Now, in the school, when we were kids, we were told an object is a one-dimensional object if it has only length. A two-dimensional object if it has length and width. And three-dimensional if it has length, width and breadth. Is that clear? We all know it. Then, when you came to university or even in the college, you were told if the points of the object, if you want to describe the points of the object, and if you need two linearly independent axes to describe, or three linearly independent axes, then three-dimensional or two-dimensional. So, number of linearly independent axes that you need to describe points of the object, the number of that axis is called dimension. That's a better definition, much better, mathematically more sound rigor. Did you ever ask ourselves why we are jumping from 0 to 1, 1 to 2, 2 to 3? Did you ask yourself, is there any object in nature which may have dimension between 0 and 1, or 1 and 2, or 2 and 3. Did you ever ask yourself? We took it for granted. All the object in nature has dimension 1, 2, 3. That's it. That question occurred to Benjamin Mandelbrot. He was born in Poland, brought up in France, and then lived for the rest of his life in America. Mandelbrot is known as the father of fractal. In fact, there are many more objects. You can recall this has a dimension 2. So none of the object can be described by Euclidean object. Euclidean object, their geometry fails to describe any of this. In fact, Mandelbrot himself said, clouds are not sphere, mountains are not cones, coastlines are not circle, bark is not smooth, nor lightning travels in a straight line. There are more objects. If you want to create an Euclidean object, we have to manufacture it, not nature. Nature, because Euclidean object is a constraint. You have to put them uniformly, highly constrained object. Constraint. Nature doesn't like it. Randomness is the thing that nature loves. And so most of the objects, the not distribution in our eyes, in our body, river basin, trees, trunk of the trees, they are not Euclidean. So we need something special to describe them. Is it clear? If there is any question, you can ask this. So if you want to slow me down, if you want to slow down me, so ask question, otherwise I may go too fast. In fact, so now, if you have an object like this, you put a grid, and this is the delta size. Remember delta to measure. So you measure how many squares contain this object. So write down the number. And then delta, make it smaller. Make it smaller. Another grid. And again you mark another number. Now this number will be higher. Make it even smaller. So keep making it smaller and smaller and measuring the number you need and plot that in the log scale. Because this one is the processing procedure to measure the ultimate dimension, not the number of linearly independent axes. Now if you take a log of n, then you find log of n equal to minus d log of delta. And that equation is equation of straight line. So log n versus log delta, and I put by mistake r. Log delta, you see a straight line. Whatever the slope is the dimension of the object. So if we measure this board by a square and make the number, obtain the number, make it smaller, delta, get the number, put in the local scale, I can assure you, you will get the slope 2. Or if it's a line, I can assure you will get the slope equal to 1. So this is the most generalized formula to get the dimension of the object. So now we can, so number of linearly independent axes is redundant. This is the most generalized definition of that. So you have to remember, this is the ultimate definition for if you want to measure the dimension of an object. Right? Second point is that mass-length relation. Still, it obeys the same mass-length relation. Only difference is that the exponent for Euclidean, it is an integer number. Now it can be a non-integer number. So if it is a, and what is the constant? Its value has to be smaller. So an object, if an object is a fractal, it must be embedded in space. Embedded in space. So if dimension of the object cannot exceed the dimension of the space where the object is being embedded. Can I make my point clear? I cannot exceed who is embedded in me. So dimension of this is always smaller, or at best can be equal to the dimension of the space where the object is being embedded. When it coincides, it is Euclidean. When it is less, it is guaranteed, regardless whether it is integer or non-integer. But typically, it is said that it is a non-integer. So if the object is embedded in a 3-dimension, and the dimension of the object itself is 2, then it is a fractal, because it is less than the dimension of the space, despite it is an integer number. But typically, it is non-integer. And now the density, you see, so mass now at the df, and the embedding dimension of the embedding space is d integer, which is greater than that. Now density is not a constant. So now if for a fractal object, density depends on the length scale you observe. It's not a constant. That is one of the signature of fractal. But a very key point that density, in the case of Euclidean, this would coincide, would be a constant. In the case of fractal, there is a dependent density. Now, the question is, this is a definite visual, what to expect when an object is a fractal. Before, it was uniform. Now it is not uniform. Okay? Just give you. This is the Mandelbrot, who is known as the father of fractal, who himself wrote 3 books. First one, the monumental book that he wrote in 1975, with which he introduced the idea of fractal. There is not one single discipline in our academia who did not use the idea of fractal. Because it's a tool that has been used even in the language, in economics, in sociology, in physics, chemistry, of course. Needless to mention, almost in every discipline, the idea is being used. Now, the question is, can we create by hand a fractal? He himself introduced in his monumental book the simplest possible fractal that you can think of is called Cantor. George Cantor, in 1806 or something like that, long time ago, he introduced a set called, now it is called Cantor set. He had no idea about fractal. He didn't know that one day it will come as an example of fractal. What he did, he wanted to show that a real number set is much more than natural number. That theory caused him a lot of trouble. You remember, you know the Kronecker physicist? Kronecker, in an open talk where Cantor's daughter was also there, like today my daughter is here. He was humiliated in front of his daughter that it is not true, because Kronecker at that time was very famous. So he went for a depression. He could not recover for that. He died out of depression because all his theory, whatever he said, it's a philosophical. So he was defining infinite. So here also I talk about a little bit of that. So he died of very depression. So not him alone. Our Boltzmann entropy you know, in his, while he was buried, he written S equal to K log omega, the definition of entropy. He also died of depression and he committed suicide because his peers, the scientists then didn't like him, the thing that he was trying to convey, message that was. Anyway, Cantor, the simplest example. What is the simplest example? You start with an interval of size 1. And you divide into 3 pieces, equal 3 pieces, and take away the middle. So how many numbers are left? 2. So n equal to 2. What is the size of each interval? 1/3, 1/3, 1/3. Next step, each of the surviving intervals, you divide in the same fashion into 3 equal parts, take away the middle and take away the middle. So you are left with 4 intervals and 2 square, and each of them has size 1/9, 1/3 square. So if you continue this, in the end state, your number of intervals is 2 to the power n. And in the end state, the intervals that are surviving, each are equal in size and their size is 3 to the power minus. Is that clear? Now I can eliminate n from this relation in favor of delta. I can easily show that n delta equal to delta to the power minus. It's 2 steps. What does that mean? Now the f is not an integer. It is then log 2 by log 3, which is 0.63, something like that. So by hand, we can create an object which may have dimension less than the dimension of the space where the object is being embedded. Where is it embedded? In a line. So embedding space is line, but the object itself has a dimension. I'm talking about 2 things. One is the object, one is the space where the object is being embedded. And the dimension of the object is less than the dimension of the space where the object is being embedded. Is it clear? What is the space of this? So, if you walk along the line, the intervals are not sitting uniformly. You see, the distance is higher, smaller, very big. If you continue, so if you walk along the object, along the line, you find intervals, although they are of same size, they are not equidistant. So if I display them, rearrange them in such a way that uniformly distributed, then it will be a line. So you see, when it is non-uniformly distributed, when the density now is not a constant because of this. Now, some special point as a passing note. At end state, my size is this. If I take df moment when it is equal to df moment, and then sum them up, I find this equal to 1. On the other hand, things that I'm throwing 1/3. I'm throwing here 1/9, 1/9, 1/9, 4/9. And if I sum them up, 1/3, 2 of them I send. So each of them size 1, and 4 of them I throw in the bin, and these, and I add them up, I get 1. So apparently, being whatever I have thrown, if I put them together, sum is 1. And on the other hand, their moment is 1. That is a puzzle still. History, we don't know the answer. So what Cantor was saying, that despite I'm cutting things away, still said it consists of infinite number. That people did not believe. That was the term that he was inviting for himself by saying that. Is it clear? My key point here is that n is exhibit power law with the yardstick with an exponent df, and this exponent is a non-integer, is less than the dimension of the space where the object is being embedded. if I have a basket full of intervals of size, each of them are same size, all of them are same size, I ask, can I create an object set? Yes, I can put one like that. In the next step, I can put one like that. The next step, I put it like this. This is creating Cantor set. So this is the Cantor set. Now, so here mass is equal to 1. Length is, I say this is the unit length. Length is also 1. Mass 2, length 1, 2, 3. And if I continue this, I find mass in the end step is 2 to the power n, and length is 3 to the power n. And if I eliminate n in favor of L, I find this relation. So again, mass length relation still follow the same law as the Euclidean object. Only difference is that this one is smaller, the dimension is smaller than the dimension of the space where the object is being invaded.
Sure.
And so,
So should there be a negative L to the power?
Yeah. No.
But are we getting back the exact same equation as we did previous time we constructed control set?
It's simple. You see, you take log L equal to n log 3.
Yeah.
N equal to log L by log 3, and you take log on this, and immediately you get. These are also typical textbook examples. So you start with the equilateral triangle, you take the middle part, and then you continue to do this. So you see, the beauty of this, I didn't mention that. If you have a line, you take a part, cut it small. I say, close your eyes, I have elongated it. Or I have taken a picture, I have blown it up. And I say, okay, open your eyes. Do you see any difference? He said, no, it's the same as before. It's called, when part looks similar, like a cauliflower. You see, in a cauliflower, you see a small part. I can dissect that small part. I can take a picture. I can blow it up. I show you. You say, yeah, this is a cauliflower. The part of the cauliflower look the same as the whole. It's a naturally self-similar. So self-similarity is one of the basic ingredients of Euclidean and fractal. In the case of Euclidean, it's trivial. In the case of fractal, seemingly disordered, non-uniform. But when you do some maths, you see they're similar. We'll see that. So this part, if you blow up, it will look like this. So part similar is important ingredient for an object to regard it as a fractal. Is it clear? Ask me if you have any problems.
Sir, I'm having trouble understanding how the iteration 1. Will it look the same if I blow it up? It's just one triangle.
Sorry?
Will it look the same if I blow it up? It's just, oh, are these?
So first step, you start with a unit interval. You divide into 3 equal parts, and you take away the middle one, and then you just draw an equilateral triangle. So you put it like this, that crossing point, you add them, take away the middle. So it's a, and then each of these you do the same, you will arrive there. And if you do the same, you will arrive here. You continue, it's beautiful card, it's called coach card. And it's also part look the same as a whole. Like this, you see, this one. And now if you blow it out, it will look the same as this. Can you see the similarity? They are self-similar. Beautifully self-similar. Now, so far as the textbook things. Now, my conclusion will come. So, nature doesn't create the way Cantor set or sequencing cartoon cascade or coach card. Because it is artificially built, either you build in the computer or you can build in a piece of paper. Nature loves probability. And no fractal appears in a blink of an eye. It takes time. So time and randomness are the two essence for nature to create natural objects. If there is, so no, nature loves, as I said, randomness, freedom to choose. So now I will incorporate a probability, some kind of probability, my randomness in my character set. So instead of dividing into 3 parts, now I will divide into 2 parts. So if I divide, start with this, I divide into 2 equal parts and take away the middle one. And if I divide into 2 parts and take away the middle part, so 1 part, if I divide, what will I be left with? Point. So that will not create a factor. What I have done is that I divided 2 equal parts and then I say with the probability P, it will stay there. And with the probability 1 minus P, I will put in a basket. So I have a piece of unit length, I have a scissor, I cut into equal parts, and one of the part, if I choose P equal to, P is your choice. So if I choose P equal to 0.5, meaning I have a fair coin in my hand, and then I toss it, I say, if it is a tail, I keep it. If it is a head, I throw in the basket. Now, if each of you, I ask, do the same, you cut into piece, and say you are, say, 1 million people. All the 1 million people I have asked to cut a piece into 2 pieces, toss a coin, and if it is a tail, keep it. If it is a head, throw it. How many? And if I add all the numbers, say, okay, now you give the number. I add them and I divide it by the million, because million number of people. That will give me average. What will be the average? And some will have 1, some will have 2 pieces. If I add a number of people they divided, I will have 1.5. So basically, consistency, you can check it. If P equal to 0, meaning you will always throw in the basket. P equal to 0, meaning you are not keeping it. What will be the dimension? You will have log 1. Log 1 equal to? So dimension equal to 0, meaning dimension of the point. If P equal to 1, that means you always keep. That means you start, you divide, and then you divide. What are you making? Still a line. You will always have dimension 1. Is it clear? So when P equal to 1, log 12 equal to 1. But in between 0, it is a factor. Is it clear? And all the other properties that I did for character set is also true here. Now I want to incorporate time into the problem. Time into the problem. So how do I do? So this is the equation that can help us. This I did in 96, 97, some of the part. So this equation means at each time I have a line. I start with the line, for example. Then I divide. How do I divide? Depend what is the choice I make. This is cardinal. And this factor is, so first of all this is the number of intervals I am watching. I am like a counter. Number of intervals of size x at time t. I call it CXT. And then I am measuring, I have a counter now, how this number is changing with time. If I have an interval of size x, if I have some of them will be peaked and broke, then it will no longer be x. So there is a lost term, that's my minus sign. Some of them will have bigger size, say y, a size y. Y can be broken such a way that one of the piece is size x, the other one will be y minus x. one of the piece will be size x, the other one will be y minus x. So it is a gain term, gain of x. That's a plus. And when x is created, it is kept with probability p. And this equation is a magic equation. You can solve it exactly analytically. And I can also solve it numerically. I can write a program and I will show you that they matches like anything. Up to many digits. So, meaning if I can simulate, simulation means what? Doing experiment. Doing experiment. Precision and highly precise experiment. When they match, that means that algorithm is the story that told by this equation. And the equation is a story. That's the beauty of analytical solution. So you can solve the solution, you can verify the solution by numerical simulation. Is it clear? So now, by choosing F, we can choose different model. So if I choose, this is the argument. Here argument Y, there are two arguments for the target. So meaning, if we add them together, that is the original particle. And this one, after you break, their sizes. So if you add them together, that means X is broken into pieces Y and X minus Y. You add them together, you get Y. Y is broken to produce a particle of size X and Y minus X. Is it clear? So now, if I choose these two products by a delta function, what will it ensure? Delta function property? Half equal part or down. So let me delta function. So now I will be expecting, if I choose this, I should get fractal dimension equal to log 1 plus b by log 2 that I. Because here also I get by getting equal to parts. So if I get the same result, that will give me some kind of confidence about my equation. And then I will go on. So, and then I will choose this, and I will choose generalized version. Is it clear for you? Next. So I choose that, I solve this, so the equation becomes like that, and I define nth moment of CXT. And I incorporate this into this equation. And so this equation becomes nth moment, rate equation for the nth moment. It's just simple. You just prove this here, you get this equation. Details is not necessary. Just try to understand the essence of the message. What is the message here? Now, you insist that there is a value of n which is a constant. If there is a value of n which is a constant, if you take derivative, this time will be 0. So I am insisting that therefore a value of n, I call it n star, equal to, if it is 0, then this cannot be 0. Only way it can be 0 on this. So if this equal to 0, immediately give me n star equal to this. It means somewhere. Say that, oh, it's very similar. Now I know this number. So, indeed, n star, before also we saw df moment, same thing, is a constant, 1, regardless the step. So here we get n moment. So n moment we'll see is a constant. 4, because that derivative equal to 0, and we found n star equal. Indeed. So if I choose the solution of this in this form, and I plug this solution into here, I get a recursion relation. I can iterate this. I can iterate over and over again. Subject to the condition that, so when n equal to n star, alpha n star should be, when I choose n equal to n star, alpha n star should be 0, because it has to be constant.
Yeah.
So I iterate this subject to the condition that alpha n star equal to 0, and then immediately I find this. And then I put this here. Now I know the solution. 3 to the power minus n star. So when n equal to n star, this is 0. And what is the value of n star? Is given by that. So I have solved the problem. And then I know that first moment is the size, mass of the system. Zeroth moment is the number. So now number, so mass and number, then I take the derivative. If you know the size, if you know the number, that is the mean size. And mean size, you know, you can find this value and you can define this. And then the power law with this. So again, so exactly df equal to this. The value for which it is conserved actually is the dimension of the system. That message has to be divided. Now, if I choose fx equal to 1 in my equation, the rate equation becomes like that. Again, if I put nth moment into this equation, the moment equation like that. Can you see? If I choose n equal to p, what do we get?
0.
N equal to p is 0.
0.
But pth moment is conserved. And in fact, after doing all the same thing that I did, I can show that with df equal to p. Fractal dimension and the conservation law are connected. The value for which the moment is conserved, that value essentially finally become the fractal dimension of the object. And so in this case, now I want to understand what is, before I know the delta function, so I divide into equals to parts. When I choose n f equal to 1, what is the rule? How do I divide? Simple. I start with an interval of size 1, and if I choose p, I have to choose by I into I, p equal to I can choose any value, say for example 0.4. I have chosen. So what I do, I pick a random number from 0 and 1. If the random number is 0.3, so I divide at the 0.3. So here, so I divide into randomly into 2 parts instead of saying equally into 2 parts. That is the difference. Now, one of the part I throw with probability 6 and I keep with probability 0.4. And that I continue. So of course, sometimes I will have this and I will have a gap. Next step, to incorporate time to my problem, I generate a random number between r equal to 0 and 1 in method. If my random number falls into this, that doesn't contain an interval. I mean, I fail to pick an interval. So what I do, I increase time by 1 unit. If r fall into this, I do the same as I did for that. And I continue to do this. If I do that, this is what I described here. So based on that algorithm which I have explained here, my students perform numerical simulation and they say GF the moment is conserved. If you do the experiment now, the value for at which it is constant, say it is this. He does the simulation again, it is constant, but numerical value is different. So if you do over and over again, each time you get a numerical value for which it is constant, you add them, take an average, you always find constant is equal to 1. This is an ensemble average. This is individual realization. Each time you experiment, the numerical value at which it is conserved are different. But ensemble average is unique, and that is always equal to 1. Right? So perfectly matches. So GF moment is a conserved. Number, log n, and n log t goes exactly as described by my equation. And log n log delta should be a straight line, slope equal to fractal dimension. So, and we know the fractal dimension is p. Whatever the value p we choose, the slope is exactly there, and it matches perfectly. So, f equal to 1 means you start with an interval, you divide randomly into two pieces, you keep one of them with probability p, and you throw it probability 1 minus p. You continue doing that, you get exactly that equation tells you. All the story that I've been told is being told. Now, one thing is missing. Is this still self-similar? That is what I'm going to answer now. So, I will need your attention now. This is more important. Okay? To do that, I will explain a little bit about. I hope you will enjoy it, because every time I do this, I enjoy it. So, it's my expectation that you will enjoy it. So, essentially, whenever we do some experiment, ultimately come down to finding something. For example, you want to find acceleration of an object. A, acceleration. It depends on
velocity,
mass and force. Similarly, you measure something that observable quantity may depend on many other quantities. So f can be a function of n number of other parameters. Like in the case of acceleration, depends on 2 parameters. And in general, I say that there are n number of parameters. Since I don't know what is f, so I say n number. Is it clear? Now, I can classify this n number of parameters into 2 groups. What is the litmus test? I say, if there are k number of parameters which have independent dimension. What is this independent dimension? Independent dimension means none of these can be expressed in terms of the dimension of the others. Like in the same way, linear axis, somebody like same definition. So I define there are k number of variables. So these cannot be expressed in terms of the dimension of the others. So these are k. So I say these k number of variables are independent. Ak plus 1 can be expressed in terms of the independent dimension. So that is the essence. If so, then say ak plus 1, its dimension is the same as I can express in terms of a1 to the power alpha 1, a to the this, that next. So now this I can call it a quantity ERT. So ak plus 1 I measure by this, so I get a number. So since this and this has the same dimension, pi1 is a dimensionless quantity. What does this dimensionless quantity means? Do you know what is the dimensionless quantity? Dimensionless quantity is a quantity whose numerical value does not vary upon passage from one unit of measurement to another.
Can you repeat?
I will. As many times as you want. So, dimensionless quantity is something whose numerical value does not depend whether you are measuring in CGS system, centimeter or kilometer or nanometer or whatever. So, if the numerical value of a quantity does not depend on the choice of a unit within the same class, of course, MPS system you cannot choose FTA, PS system. Within the same class, the numerical value, if it does not vary, changes upon transition in one, for example, a circle. Circumference divided by diameter. Length by length is a dimensionless number. Now, this numerical value, it does not depend, will not depend on the size of the circle. in one unit of measurement to another. Essence same. Is it clear? So dimensionless quantity, which is very important for my rest of my talk. So I must make you understand what it is, and you can appreciate the importance. Its importance can hardly be exaggerated. It is so important. Is it clear? So a dimension. To understand what is dimensional quantity, you have to understand what is not dimensional quantity. A dimensionless quantity is the quantity that numerically doesn't change. I'll give you an example. I have 3 triangles. I want to measure S. So S is my observed quantity, observable quantity that I want to measure. So S obviously it will depend on A, B side of the series. So obviously I can put it in a function like that. Just to magic like this. I put it like that. Okay? Okay. Now, you see what I am doing, I will change this and I measure, I will change the B. So B is small, I measure the area as a function of B. So if I measure S as a function of B, the area of 3 triangles is like this. Of course, because the area equal to half AB. Half AB. So I plot S versus B. The slope is half A by 2, and you see that depending on their side, the slope is changing. Fine. Now the same data, if I all the area, when this area is divided by C square, this area is divided by C square, hypotenuse, the area is divided by C square, and now I plot as a function of B by C, which is a dimensionless quantity, B by C, S by C square is also a dimensionless quantity. All the 3 data collapse into one. What is the significance of that? It implies the triangles for a given B by C, the numerical value does not depend how big the triangle is. The numerical value is the same value. If it is so, the triangles are say similar. So when you get data collapse, the significance of this, I give you a simple example here. Actually, simple example is not possible. So simple example, what is the significance when you get a data collapse? What is the message? Takeaway message that when you get a data collapse, corresponding system phenomena is similar.
What is the y-axis of the second graph?
S by C square. Yeah, it is too small font. This is fault. Is it clear? Okay, fine. But this is the custom it's not my part. Now is my part. I C is a function of ht. I see that my mean particle size delta is inverse of time. So this is mean particle x and inverse of time, they must be the same dimension. So the ratio of this, I just call it Z to make general, right? Is a dimensionless quantity. So if x can be expressed in terms of time, c itself also can be expressed in terms of time, because if x is a function of time, then c itself, and any physical quantity is always a polynomial law. So if c, that means c must be like t to the power theta, if it depends only on time. So their ratio is also a dimensionless quantity. So now I want to pi theorem CHT, I can write it like that. So I have 2 variable problem turns into a 1 variable problem. What is the advantage? If I have a partial differential equation, already an enormous simplification. Solving an ordinary differential equation is much simpler than solving a partial differential equation. So that is the advantage. Indeed, if I plug it into my equation, this is the equation for f equal to 1. If I plug it here, this turns into an ordinary differential equation of 1 variable. So, and I differentiate one more time to get rid of this integration. And finally, just if you change the variable, I get this equation which maps with the Kumar's confluence function, hypergeometric function. So this is the solution of this equation, and the asymptotic solution is this. So if I know phi theta, I can plug it here, and theta is fixed by the conservation law. You know that gate moment is conserved. If I apply that, I get theta equal to 1 plus p. So I have the complete solution of the equation this. And indeed, now what does it mean? If I C divided by t to the power 1 plus p would be the dimensionless quantity. X by xt, because this is the dimensionless quantity, z equal to -1, so xt is the dimensionless quantity. So now simulation says CHT versus X I plot. So I have a system, I took it, and then system is evolving with time. So evolving with time. Time started. At given time, I took a snapshot. I measured C as a function of X. So I plot. Again another time, I plot. So each time I took a snapshot, I plot. They are distinct. Now the same data, I just plot in the log dimensionless parameters. All these data collapse into one. But three triangles, they are similar. The same system, as it is evolving with time, any snapshot you take, all are similar. So systems are evolving in a self-similar fashion. Self-similar. Like cauliflower, part of it looks the same as a whole, and fractal, one of the essential ingredients is a self-similarity. So we found it is also self-similar. Is it clear, Professor?
Question?
Yeah.
The last part of the second graph, it looks a little like
Noise, because the randomness. So if you take more and more and simple average, and if you take longer and longer time, then noise will disappear. But that noise, because of the inherent randomness in the problem. It depends on the ensemble size. If you increase the ensemble size, the fluctuation will decrease. So it will go away. Now, what happens instead of choosing one, if I choose x, y to the power theta? So I can do the whole things all over again. Constant. I had puzzled for few years, not only me, all the scientists who consider this kind of solving this kind of equation. What is the when beta equal to 0, we know that f equal to 1, same. But beta equal to 1, what are the rules to divide? How can I simulate? Beta equal to 2, what do I do? Beta equal to 3, what do I do? I had this problem. And for many years, when I was searching for an answer, finally I found an answer. So one thing is that I can plug this into this equation and again nth moment. In this equation, I get this solution. I can again insist there must exist a value of n for which the corresponding moment is a conserved quantity, meaning the derivative will be 0. And only way it can be 0 if this is equal to 0 because it cannot be 0. So by setting this equal to 0, I can solve a polynomial equation, I get the root. Real positive root will be correspond to the conserved quantity. And indeed, as for a p equal to 0.75, for beta equal to 0, I get the factorization 0.75. Beta equal to 1, I get this value. Beta equal to 2, I get this value. You understand? You see the sequence? As I increase the beta value, so and we also know that the value of n star for which it is conserved is ultimately the fractal dimension. So fractal dimension is increasing as I am increasing beta. What happens in the limit? Beta tends to infinity. I can apply the Stirling approximation. I get beta tends to infinity and star equal to log 1 plus p by log 2. Is it familiar to you?
Yeah.
What does it mean then? In the limit beta tends to infinity, I am dividing the interval into equal parts. That's why it is producing this. So now I can see beta equal to 0, totally random. Beta equal to 1, randomly this is less. And increasing it and randomness is totally sealed in the limit beta tends to infinity. Is it clear? Now, how do I choose? Then I was reading a book on chaos. There is one equation.
Sir.
Yeah? What time do you talk?
So there's another person after you. We'll have coffee break after this, and then there's another person after you. Before.
Okay. Give me a few minutes.
Okay, fine.
If you are kind enough. I start late. Okay. This equation is important. It's called bifurcation. So, what happens when you have a x n equal to r x n minus 1, 1 minus x n minus 1. So, what happens if it is r equal to 2? It comes from population growth. You see, point x n plus 1 equal to r x n you choose. That means next year's population is the previous year's population times r. It is increasing, unlimited increasing. So that is a problem. So resource is limited, and once population will grow up some extent, they will fight and they will extinct. So it is not possible the population of anything will grow, continue over and over again, ad infinitum. So in order to restrict to some extent, so you put x. That is the practice required. Now, if you choose r equal to 2, and initially x not equal to say a random number, 0.00001, and if you iterate this over and over again, you reach to, if you iterate this, I started with this 0.5. So there is a fixed value. No matter what the value is initially choose, it will always reach for 2. But if you continue the value, so we start for 2, it is 0.5, and then it increases. 0.3, it is alternate. There are two values. If you repeat, you will get one value. You repeat again, you get another value. You repeat again, you get this value. So and then if you further increase, you get double again and continue. At some point, 3.57, it is a chaos. It's a such a way, it's a like butterfly effect. So initial value that you choose, small change can have enormous impact in the final outcome. That's why chaos comes. Anyway, that is not my point today. Today is that for r equal to 2, I wanted to reach to a 0.5 value because I have exactly two equal parts. I used that. So in the case of f equal to 1, I just choose x naught. Right. In the case of beta equal to 1, I only iterate 1. Then I pick a random number, I iterate one time, whatever the value I get, I divide. If beta equal to 2, I iterate 2 times. Beta equal to 3, I iterate 3 times. Okay? And then in that way I fashion. And indeed, beta equal to 1. So beta equal to 0, beta equal to 1 is equal to everything that I have, my analytical solution conforms everything by the numerical simulation. Beta equal to 1, see actually before like that, I can do the data collapse over again and it continues like that. Okay, now. So I will leave it for you to read since he said that I don't have time. And also if you have questions, please. There's no question? Okay.
So you if I'm looking for Euclidean space, right? For
Sorry?
Euclidean geometry,
And
is it is there any indication or way to extend to non-Euclidean cases like Gaussian geometry or Wajorowski geometry?
no, their own geometry I don't know. I'm not.
Okay, non-Euclidean, in general, non-Euclidean.
So my point is that here I invoke only Euclidean just to understand fractal.
Yeah.
So even Euclidean is not my part. So to let you understand the difference between the two. So if you want to understand one thing, and a better way to understand this, how does it differ from its Euclidean counterpart? That is the only thing I will do. Did I answer your question? No. But the other geometry I don't know.
But I think basically the metric signature is different. Euclid all same sign, so that is equal geometry. You have some plus sign, some minus sign, like a correct delta. You can mu. All same sign, correct delta. Different sign is a metric space.
Anyway, a passing note, chaos can be better understood by using the tools fractal and multifactor. Multifactor I didn't touch today because it's more complicated, but I thought this today's audience, first I should discuss about fractal. So, so it's important. As I say, in every branch of science and social science, in economics, in language, this idea of fractal are being used. You will not find, even Robertson FRW equation, metric. That metric, one of the fundamental assumptions is the universe is mass distribution uniform. But Luciano Petronero, an Italian scientist, he is the leader of a school of thought. He said that mass distribution of the universe is not and cannot be uniform. If it is not, if it is a fractal, you have all lot of challenges in front. So, but that is still a long debate about it. And I see there is no reason why the universe has to be Euclidean. The universe is more likely to be a fractal in my view. But I agree with it narrow. But there are people who think that in the long range, they regard it as a uniform. But how long and how is a question of only one simplicity that's right.
So I have a question about the integral differential equation that you use. So that comes from different paper or you revise it?
No, it was say 100 years ago, but I extended it to a higher dimension last time. In 97, I can use that, I extended it for 2 dimensions. And that 2 dimension is much more interesting because that's the multifactor.
So initially it was for 1 dimension.
Okay. Thank you very much.